Hi students. In the last lecture, we have discussed about simple pendulum. Now in this lecture, we are going to discuss compound pendulum. Let us see what is now compound pendulum. Now it is any rigid body which is free to rotate. I am repeating, any rigid body which is free to rotate is called compound pendulum. Let us take diagram here. Let us take, it can be any shape. It is now fixed somewhere here. Assume that it is in equilibrium position initially. Equilibrium means center of mass must be exactly below the point of suspension. This is the first condition. Center of mass must be exactly below the point of suspension. So we are taking a rigid body. It can be any shape. It is free to oscillate in a vertical plane, and axis of rotation is now horizontal. Now displace this body, or you can say rotate the body through a small angle theta. Let us take the line joining the point of suspension and center of mass rotates by angle theta. So here we are rotating the rigid body. It is anti-clockwise by some angle theta. Then the line joining point of suspension and center of mass rotates by same angle. Now see who provides restoring torque. So here you can see now force acting on center of mass, that is mg downwards. If you observe only center of mass, it is following now a circular path, right? Now take its a component along the tangent, that is mg sin theta. Because of this force, torque will be clockwise. So we are taking now torque about point of suspension. So torque about this point will be mg sin theta into separation between point of suspension and center of mass. Let us take it as d. So we are taking the separation between point of suspension and center of mass as d. Then torque will be, so coming to here, torque will be, it is mg sin theta into d. And this is now net torque, that is equal to I into alpha. And here we are taking this theta is very small. So since theta is very small, sine theta approximately equal to theta. I am writing here. So since theta is very small, sine theta approximately equal to theta. So writing that value here, then alpha equal to minus mgd by I into theta. See, it is of the form minus omega square into theta. That means now omega square value is known. So from that we are going to get expression for time period. That is t equal to 2 pi root of I by mgd, where d is the distance between point of suspension to center of mass, and I is moment of inertia of that rigid body about point of suspension. So this is no expression for time period of a compound pendulum. Let us take one problem basing on this. See the question. A uniform thin rod of mass m, length L is free to rotate in vertical plane and axis is about an axis which is a horizontal and passing through its upper end. Find period of small oscillations. So it is given a uniform thin rod. So uniform thin rod, I am making a diagram here. Uniform thin rod suspending at the upper end. A uniform thin rod suspended upper end. Center of mass will be at midpoint. That means D value it is L by 2. If we rotate now this rod to a small angle theta, then it makes oscillations. Now in this case, I value. See what is I value? Since it is a rod, a thin rod, oscillating about one end. So rotating about one end of the rod. Then I value, it is ml square by 3. And coming to D value, it is L by 2. It is a uniform rod. So center of mass will be midpoint of the rod. So substitute values here. In the place of 5, ml square by 3. In the place of mg, in the place of d, L by 2. So final answer is T equal to 2 pi root of 2L by 3g. So this is time period of a uniform thin rod when suspended at one end. So if you are changing this suspension point, then D value changes accordingly. Accordingly, I value changes. Okay, right. And if you see simple pendulum, it is one special case of compound pendulum. See how is that? If you take simple pendulum, how we get the answer? In case of a simple pendulum, we have taken string is massless. Therefore, I equal to ml square, simply having a point mass. And d equal to L. Now substitute these values. So T equal to 2 pi root of, in the place of phi, ml square by mg. In the place of d, it is, so m gets cancelled, 1 L gets cancelled here. Remaining is now 2 pi root of L by g. So it is simply one special case of compound pendulum. Okay, right. Here you can observe one more question. It is like where the rod should be suspended so that time period of oscillations may be maximum or may be minimum. Suppose you are fixing at some distance x from the center of mass, means from center of the rod. Then for what value of x, time period of oscillations will be maximum or minimum. Means we have to cross check that is it maximum or minimum. Okay. So then what we have to do is find I value about same axis. I am writing here. Let us take, this is now uniform rod. suspending at a distance, the point of suspension at a distance x from center of mass. Then see where change comes. So while calculating I value, so I value I value must be it is ml square by ml square ml square by 12 plus this is square plus mx square. So we are taking point of suspension is at a distance x from center of mass. Then I value becomes ml square by 12 plus mx square. And in the place of d, write it is x. Substitute these values in that, differentiate and make it equal to 0. Then you get the value of x for which t becomes either minimum or maximum. Okay, you can try that of your own. Let us go for next one. Let us see some basic problems related to simple pendulum. See the first question. If time period of a simple pendulum is 2 seconds, known as seconds pendulum, then find length of the pendulum. So take g equal to pi square. So you are given now time period is 2 seconds. It is known as seconds pendulum. We have to find length of the pendulum. Then see expression is t equal to 2 pi root of L by G. So t value given 2 seconds, 2 equal to, it is a 2 pi root of L by, in the place of G, condition given, take pi square. Therefore, pi and here pi square gets cancelled, 2 gets cancelled. That implies length equal to 1 meter. That means if time period of a simple pendulum is 2 seconds, its length will be approximately 1 meter. Okay, right. See the next problem. If a simple pendulum is suspended from the ceiling of a lift, which is having acceleration A, then period of a small oscillations is 2 pi root of L by G plus or minus A. See how to get this one. So when it is in a lift, when we see from ground frame, simple pendulum moves along with the lift at the same time. It makes oscillations inside the lift. That means motion what we observe from ground frame is combination of these two. But if you observe from lift frame, then we can see only oscillations. So we are solving the problem from lift frame. Now since lift is having acceleration, we have to take pseudo force. So I'm making a diagram here. This is now simple pendulum which is inside lift, mg downwards. Suppose acceleration is upwards, then pseudo force will be downwards. So mg plus ma, right? That means now in the place of g we are writing it is g plus a when acceleration is upwards. If acceleration is downwards, then writing in the place of g it is g minus a. Like this we can solve questions in lift frame. Now see next problem. A simple pendulum is inside a liquid of density rho L. Then period of a small oscillations is, see how to get it. Let us make a diagram here. So taking a simple pendulum, let us displace through some angle theta. See how many forces acting on the particle. One is mg downwards, tension along the string towards suspension point, and next one is buoyancy force vertically upwards. So earlier when we discussed, there was only tension and weight mg. Now one extra force is buoyancy, which is vertically upwards. Now take a restoring force. See how to take it. So here restoring force. We have one component is mg sine theta, and here component of buoyancy force. This also it is now b sine theta. Now restoring force is equal to minus of mg minus buoyancy force into sine theta. Okay. Buoyancy force is mg minus buoyancy force into sine theta. And theta is very small, writing simply theta in the place of sine theta. Now remaining simplification here, take mg outside. It becomes now 1 minus rho L by rho B into theta. So it is now of the form minus k. Do one thing in the place of theta, right here, in the place of theta right here, it is x by L, where x is now here displacement. Okay. So it is of the form minus k into x. So in the place of x, see what we have now. It is mg into 1 minus rho L by rho B by L. So then substitute that value here in the place of t equal to 2 pi root m by k. In this expression, in the place of k, substitute now that value. Then we are going to get that expression, right? So finally, this is the answer. So this is the final answer. That means in the place of g, we are substituting g into 1 minus rho L by rho B. G into 1 minus rho L by rho B. Okay. Right. Let us move to the next one. A simple pendulum of length L suspended from the ceiling of a car which is moving with a constant acceleration A on a straight horizontal road. Find a period of small oscillations. So given it is in a car, I'm making diagram here. It is inside a car. And car is having acceleration J, which is a constant. Now again, solve this problem from car frame. Because in car frame, we can see only oscillations. But car is having acceleration, which is non-inertial frame. Then we have to include pseudo force. Then see, in equilibrium, this makes some angle take it as theta naught, mg downwards. Pseudo force is left side and tension will be along the string length, right? When it is in equilibrium, tension balances resultant of pseudo force and gravitational force. That means in equilibrium, tension equal to m into square root of g square plus a square. This is a tension in equilibrium. Okay, right. Now we can see oscillations are always about mean position. That means now in this problem we can see pendulum oscillates about this position like this. I am showing here oscillations about this point. This is a new equilibrium position. Oscillates like this. So we are replacing the value of g with square root of g square plus a square. Right? That is what we have written here. In the place of g, writing square root of g square plus a square. Okay. Next. See the next one. If the car moves with a constant speed in a horizontal circle, then period of a small oscillations is. See now here only changes in the place of a in the above problem. In the place of a, right here v square by r, which is centripetal acceleration. That is the only change. Remaining is as it is. I am repeating. In the place of acceleration a, right now v square by r. Therefore, it is now square root of g square plus v square by r whole square. Okay, right. Let us see now next problem. Next one. If a simple pendulum is suspended from the ceiling of a car which is moving down an inclined plane of inclination alpha with a constant acceleration g sine alpha, then period of a small oscillations is 2 pi root of L by g cos alpha. See how is it? So I'm making diagram here. Inclination it is alpha. There is a cot which is moving down with acceleration. This is now simple pendulum. I will make separately here simple pendulum. Now simple pendulum will be normal to the inclined plane. See how is that? Writing here mg components down the plane. Mg sine alpha. And since we are solving the problem from that car frame, take pseudo force which is up the inclined plane, that is mg sine alpha, mg, just a minute. It is mg sine theta, and these two are now cancelled. So it is alpha, not theta, alpha. So mg sine alpha and this also same. So both gets cancelled. There is no net force along the inclined plane. Now only net force it is, we can say weight component is normal to inclined plane. That is mg cos alpha, right? That means here we are replacing the value of g with g cos alpha. This is now mean position. That means string is now normal to inclined plane and it oscillates about that position. It oscillates like this. It is normal position is, sorry, mean position is normal to inclined plane. Okay. So simply replace g value with g cos alpha, right? Let us go for next problem. See the question carefully. A cube of side length L is placed on a horizontal surface. Its bottom face is fixed. It is fixed to a horizontal surface. A block of mass m is placed on its top face. A parallel force, a force parallel to upper face is applied to m and then withdrawn. Then it's a period of a small oscillations is. See the diagram for this. Diagram for this is just a minute. Yeah, let us make the diagram here. This is a cubical block. We are fixing the bottom face to the surface. Place a block on the top face. We are applying force to the block parallel to this upper face. Then this shape becomes like this. Let us take this angle is now angle is a phi. Suppose this displacement is x. Okay, we are knowing that shear strain shear strain equal to x by side length is l, right? Now see what is the restoring force. So taking here shear modulus equal to F by A, that corresponds to shear stress. X by L corresponds to shear strain. So from this F equal to minus eta A by L into X. And why we have taken here minus? Because displacement is now towards right side, but the force is now left side. That's why we have taken here minus sign. And in the place of area, we can write L square. Then we are going to get eta L into X. So in the place of force constant, it is now eta into L. So time period is now 2 pi root of m by k. In the place of k, it is eta L. Okay, right. Let us see now next problem. A cylinder of length L of cross-section area A, mass m, density rho b, is floating in a liquid of density rho L. If it is slightly depressed and released, then find its period of oscillation. See diagram here. Suppose this is surface of liquid. This is a cylinder with a some part inside. It is now floating. Okay, we are given length is L. So since it is a floating, its weight will be balanced by buoyancy force, right? Now condition is given that slightly depressed and released. Suppose its displacement is x from mean position. Okay. Suppose x part of the cylinder is going inside. Then corresponding to x, we are having extra volume inside liquid. And for this extra volume inside liquid, we are getting extra buoyancy force. I am repeating. If you take x length inside extra, then extra buoyancy force will be the restoring force. See what is now extra buoyancy force. The restoring force is now extra buoyancy force. Extra volume is A into X, extra volume. That volume into density of liquid into G. I am writing here extra buoyancy force is providing restoring force. I have written here. The extra buoyancy force provides the restoring force. So this is now extra volume into density into G. So rearrange now. So F equal to minus something into X. So in the place of force constant, it is now A into density of liquid into G. Now substitute here. T equal to 2 pi root of M by K. In the place of K, A rho L G. So this is answer in terms of mass of the cylinder and density of liquid. Suppose if you want to express in terms of length of cylinder, then what we can do is in the place of mass, in the place of mass, you can write area into length, that is volume, into density of body. So area gets cancelled. Remaining is now 2 pi root of L into density of body by rho L into density of, rho L into acceleration due to gravity. So this is in terms of length of the cylinder. So either we can take in terms of length of cylinder or in terms of mass of cylinder. Means if you are given mass and density of liquid, write M by A rho L G. If you are given length and density of liquid, density of body, then we can use this result. Okay.